Hello students, this is Neha Mathur and today I will tell you about the asynchronous down counter, which is itself a most important classification of counter. Counter, which is a digital circuit used to count number of pulses. So any digital circuit which is used to count the number of clock pulses is said to be counters, and today I will start with asynchronous down counter. But before start the topic, I will tell you about what is counter actually and the proper classification of counter. Since a counter which is also a sequential circuit and used to count the number of pulses, on the basis of its application, on the basis of its definition, counter is most important application of flip-flop. So before understand the proper concept of counter, you must have idea about the what is flip-flop actually. Flip-flop having SR flip-flop, JK flip-flop, T flip-flop and D flip-flop. Here for the designing of counter we will take JK flip-flop. So before start the proper concept of counter, you must have knowledge about how what is flip-flop actually and how flip-flop works. Because for the designing of counter we will take JK flip-flop. Fine. So now back to the topic. Counter which is used to count the number of clock pulses having classification on the basis of applied clock pulses. So on the basis of that, counter has two types. The first is synchronous counter and the other one is asynchronous counter. Asynchronous. So the first type is synchronous and the second type is asynchronous. What is synchronous counter and what is asynchronous counter? Always remember, whenever you will go with the designing of counter, you will have to apply clock pulses. So how you will differentiate between synchronous and asynchronous? If you are going to design 4-bit counter, then you will have to take 4 flip-flops, and if you want to go to design 3-bit counter, then you will have to take 3 flip-flops. And for individual flip-flop, if you are going to deal with individual clock pulses, then such type of counter is said to be synchronous counter. While if you are going to design with a counter in which only one clock pulse is required, which is applied to the first flip-flop, while there is no need to apply separate clock pulses for all the flip-flops, thus the type of category comes under asynchronous counter. I am again trying to explain this. Suppose you are trying to design 4-bit counter, that is you are going to take 4 flip-flops. So if you have 4 flip-flops and for individual flip-flop you have 4 clock pulses, thus such comes under the category of synchronous counter. While if you have only one clock pulse to initiate or to start for first flip-flop, such comes under the category of asynchronous flip-flop. So if you have only one clock for the first flip-flop, while for the other flip-flop you will proceed with output of first flip-flop to the input of second flip-flop in terms of clock pulse. So whenever you have only one clock, just to initiate the first flip-flops comes under the category of asynchronous, while if you have individual clock pulses for all the flip-flops, such comes under the category of asynchronous. So counter may be synchronous or asynchronous. On the basis of their application in terms of clock pulses, counter has 3 types. The first type counter is said to be up counter, while the second one is down counter, and the third category is up down counter, or a counter which is used to count up numbering as well as down. So as the name indicates, the first classification is up counter. This counter may be synchronous or asynchronous. This is a different concept, but what is up counter is actually a counter which starts from lower digit and going toward higher digit. Just example, a counter counts to start from 0 or count from 7, or you can say 0 to 15. Such type of counter is said to be up counter. Fine, start from lower digit and going up to higher digit. Similarly, what about the down counter? A counter which starts from higher number and come toward lower number. 7 to 0 or 15 to 0. Why I am taking such random numbers? Just because the concept of binary numbers. Because if you have 3-bit combination, then it will 2 raised to the power 3 is equals to 8. So 0 to 7. If you have 4-bit combination, then 2 raised to the power 4 is equals to 16. So it will be starts from 0 and go till 15. So up counter starts to count from lower digit and count till higher digit. These digits are not fixed. This may vary from 0 to 7, or if you want, you will start from 0 to another digit, but the lower digit will be small while the higher digit will be large. Similarly, in the concept of down counter, the lower digit will be higher and the second digit will be low. Fine. And what about the up down counter? Up down counter is a digital circuit which is capable to work for both the concept. It can work as well as up counter as well as down counter. There will be only one circuit, but if you want to go to proceed as an up counter, then you can operate this for the classification of up counter. Similarly, you can go with down counter. So synchronous and synchronous counters can have 3 types: up counter, down counter and up down counter. Today I will tell you about asynchronous down counter. So firstly you must clear with the topic actually, that is asynchronous. That means I will start with one clock that is applied to the first flip-flop. Next, down counter, that means whatever we will design, it will start from higher digit, or I can say higher number to lower number. Fine. So a flip-flop with a counter which starts to count from higher number and going toward lower number comes under the category of down counter, and only if one clock pulse is applied to the first flip-flop, that is said to be asynchronous down counter. So now we'll start with asynchronous down counter. In order to understand the proper designing of the asynchronous down counter, here I am going to design 3-bit down counter. 3-bit, that means 2 raised to the power 3 is equals to 8. That means this flip-flop is capable to count total 8 numbers, and the number starts from 7 and 8 and end 8 0. So 7 6 5 4 3 2 1 and 0, total 8 digits. And since it is a down counter, so the counting will start from 7 and proceed with 7 6 5 4 3 2 1 0, and the process is recycle, so it will work in recycling manner, 7 to 0 and again 7 to 0. Until unless clock pulse is applied, it will work. So we are going to design a 3-bit down counter. Fine. Since it is capable to count 8 digits, starts from 7 to 0, but in terms of binary digit, how I will represent? See, 7 6 5 4 3 2 1 and 0. This is the actual cycle, and it will again start from 7. But what about the binary representation? In terms of binary representation, 7 is always represented by 1 1 1, while 6 is with the concept of 4 to 1. I am using the concept of 4 to 1, and then I am converting these decimal numbers into equivalent binary numbers. So for the representation of 6 into its equivalent binary number, it will be 1 1 0. Again, for 5 it will be 1 0 1, for 4 it will be 1 0 0, for 3 it will be 0 1 1, for 2 it will be 0 1 0, for 1 it will be 0 0 1, and for 0 it will be 0 0 0. So this is the binary equivalent representation of 7 6 5 4 3 2 1 0. Fine. Now we will design 3-bit asynchronous down counter, and the counter is always designed with the help of flip-flop. Since here we have 3-bit down counter, so how many flip-flops are required? 3 flip-flops are required to design 3-bit down counter. And what about the type of flip-flop? Here we will go with JK flip-flops, just because the property of toggle. We may have the option of SR flip-flop, JK flip-flop, T flip-flop, D flip-flop, but for the designing of down counter, JK flip-flop is most preferably preferred, just because the property of toggle. Fine. And if you remember the concept of registers, which is also an application of flip-flops, for the designing of registers, T flip-flop is always used. Fine. So now D flip-flop is always used for the designing of register, whether it is a CISO, PIPO, PISO or CISO, D flip-flop is always used, while for the designing of counters we will go with the JK flip-flop, and I am again repeating because of its toggle property. Fine. So since we are designing 3-bit down counter, so what is the actual, how the designing will start? The designing will start with number of flip-flops. Since this is the 3-bit, so we will take 3 flip-flops. Flip-flop 1, flip-flop 2 and flip-flop 3. JK flip-flop having 2 inputs represented by J, K, 2 output Q and Q bar. Similarly for this flip-flop, 2 inputs J, K, output Q and Q bar. Similarly for the third flip-flop, input is J, K and output is Q and Q bar. Now this flip-flop I am taking the name flip-flop A, while this flip-flop is flip-flop B and this is flip-flop C. Now as per their naming, now I will convert this input J as a JA, similarly KA, QA and QA bar, because this flip-flop is flip-flop A, and for the flip-flop B the input is JB, KB, QB and QB bar. And what about flip-flop C? JC, KC, QC and QC bar. Fine. Here I am taking 3 flip-flops. Now what about the clock? Here I am using clock. See, bubble is using here, that means the circuit will work for the negative pulse of the clock, or I can say for the negative aging of the clock. Here I will take clock. Now since this is a asynchronous down counter, then I will not take 3 separate clock pulses for these 3 flip-flop. I am again repeating, there is no need to take 3 separate clock pulses for these 3 flip-flop, just because it is a asynchronous down counter. I will only apply directly 1 clock from here. Now what about the clock for second flip-flop? The output of the first flip-flop will work as a clock for the second flip-flop. Similarly, the output in terms of complement, that is QB bar, will work as a clock for the third flip-flop. If we have 4-bit asynchronous down counter, then we'll go with 4 flip-flops. Then the output of third flip-flop will provide the clock to fourth flip-flop. So I am again repeating the concept of asynchronization, that is only 1 clock pulse is required, or only 1 time clock is applying here directly, while for the application of this clock I am taking the output of this, while for this clock I am taking the output of second flip-flop. Fine. 3 flip-flops, flip-flop A, flip-flop B and flip-flop C. Now what about their main inputs? That is JK, JK, JK. Here I am taking one logic which is set at binary number 1, logic 1. Now this logic is applied here for both the inputs. Flip-flop A having 2 inputs J and K, both are connected with logic 1. Similarly, the second flip-flop, both the inputs JB and KB is connected with this logic. Similarly, JC and KC is again connected with logic 1. Fine. So all the flip-flops in terms of their direct input JA, KA, JB, KB and JC, KC is directly connected with logic 1. While the clock is applied directly for the first flip-flop, while for the second and third flip-flop I am providing the output of previous flip-flop. This is the proper circuit and this is the QC, which is the output of third flip-flop. QA is the output of first flip-flop, QB is the output of second flip-flop and QC is the output of third flip-flop. This is the circuit diagram of 3-bit asynchronous down counter. Now what about their operation, or how I will start? Before start the operation of this circuit, I am again repeating, I have 3 flip-flops, flip-flop A, flip-flop B and flip-flop C. Since the JK flip-flop has 2 inputs J and K and 2 outputs Q and Q bar, but this flip-flop is flip-flop A, so their input will be represented by JA and KA. Similarly, their output will be QA and QA bar. And what about the second flip-flop? For the second flip-flop, the inputs is JB and KB and the output is QB and QB bar. Similarly, for the third flip-flop, input is JC and QC and the outputs are QC and QC bar. Now here I have 3 separate outputs for 3 flip-flops represented by QA, QB and QC. Fine. Now what about the clock? Since it is a asynchronous down counter, so I have one directly clock applied at the first flip-flop, while the output of first flip-flop, which is QA bar, is connected to the clock of second flip-flop. Similarly, the output of second flip-flop is connected to the clock of third flip-flop. This is the general procedure. If you are going to design the 4-bit flip-flop, then you will have to add one more flip-flop, naming flip-flop D, and their input will be JD, KD and the output will be QD and QD bar. This is the circuit diagram. Now I will start the operation. So initially before start the operation, since the operation will start with each and individual clock pulse, which is represented by like this. This is the clock, and since we are going to design 3-bit counter, that means we'll have to take 8 clock pulses for the successful completion of this operation. Now as we'll start the operation, the first important step is initially set all the flip-flops at reset condition, that is QC, QB and QA is equals to 0, 0, 0, reset state. Initially let us assume that all the flip-flops are in reset state, that means QA is equals to 0, QB is equals to 0 and QC is equals to 0. This is the first important step. Now as the clock pulse is applied, as the clock is applied, I am again repeating, since the bubble is used, that means the circuit will flip-flop will work for the negative edge of the clock. That means it will work for the falling edge of the clock. So as the negative pulse is applied, this flip-flop A will start and flip-flop A starts to toggle. And as per the concept of toggling, initially if the output of the flip-flop, which is a QA, is set at the value of 0, and because of the toggle, now QA become 1 and QA bar starts to change state from 1 to 0. And as this QA bar starts to change state from 1 to 0, the 0 is applied at this second flip-flop. Since the bubble is again here, then the again 0, when 0 comes here, the bubble converts this 0 into 1, and as the 1 is applied to flip-flop B is also starts to work, and now QB, which was initially 0, because of the property of toggle, it will set at 1, and QB again start to change its state and it will 1 to 0. Now again QB bar, which is again connected with flip flop C. Now again Q0 is coming from here to here. Bubble will convert 0 into 1 and again flip flop C starts to work, and QC, which was initially 0, will become 1 because of the property of toggle, and QC is equals QC bar will again change state from 1 to 0. So these three steps, step 2, 3, 4, these three steps are representing the individual working of these three flip-flop. The first step is common, which is the step to reset all the flip-flops, which I did by reset this 0, 0, 0. Fine. So before the completion of the working of these three flip-flop, now I have output QA is equals to 1, which was 0, QB is equals to 1, which was 0, and QC is also 1, which was initially 0. So now you can easily observe that after the complete cycle of these three flip-flop, now you have QC, QB and QA is equals to 1, 1, 1. That means 7. So if initially your flip-flop is set at 0, now it will start to count 7. Fine. Now again back to the next stage. Now you have the next step when you set these three flip-flops at 1, 1, 1, 1, 1, 1. So as the next cycle of the clock is applied, that is this one, all these three flip-flop will start to work, and now you have the previous values is 1, 1, 1, which will be now 1, 1 and 0. Fine. And as these three, 1, 1, 0, that means 1, 1, 0. Since this flip-flop is set, QA is set is 1, because of toggle it will 0. Since QA will 0, QA bar will change its state from 0 to 1. Fine. Similarly, QB is equals to 1 and QB bar will change its state from 1 to 0. Fine. So the next cycle is 1, 1, 0. So now you have 1, 1, 0, which is for the number 6. For the number of clock pulses, now if we will go with the third clock pulse, you will have the combination of 1, 0, 1, which is for 5. So the number of steps will repeat again and again until you will apply the clock, and you will have to apply the clock for the 8 times, because you are going to count 3-bit asynchronous counter. That means you are going to count 7 to 0. That means total 8 digits. So you will have to apply 8 number of clock pulses, but there is no need to represent the complete operation. Just go with the one cycle, that is initially set QC, QB, QA is equals to 0, 0, 0. Fine. Now as the first clock is applied, QA will 1 and QA bar will change state from 1 to 0. Similarly, QB will 1, since it was 0, now it will 1, and QB bar will change its state from 1 to 0. Similarly, QC, which was 1, it will 1, which was 0, it will 1, and change its state from 1 to 0. So the initial values is converted into 1, 1, 1, and the counter starts to count from 0 to 7. Similarly, the number of steps will repeat 8 times, because you are going to count 8 digits, but there is no need to represent all the steps. It is sufficient to represent these 3 steps, which is the complete cycle for these 3 flip-flop. The same operation is repeated 8 times to represent the complete cycle. Fine. So this is the general working of the 3-bit asynchronous down counter. One more important thing is you should complete idea, or you also must have the knowledge about the timing diagram of this. Now I will go with the timing diagram of asynchronous down counter. So now I am going to draw the timing diagram of 3-bit asynchronous down counter, but before start this I am going to draw a table. If you are clear with the concept of this table, then it will be easy to draw the diagram. See, here you are going to design, you are going to count 8 numbers starts from 0 and end at 0. So your decimal numbers are 7, 6, 5, 4, 3, 2, 1 and 0. Fine. You have 3 flip-flops and their output is represented by QC, QB and QA. Fine. These are your flip-flop outputs. Now 7 is your maximum number and this is the direction of counting. Direction of counting. Since this is a down counter, that's why this is your direction 7, 6, 5, 4, 3, 2, 1. Now when you will apply number of clock pulses 8 times, then what will be the actual output? For the 7 it will be 1, 1, 1. For the 6 it will be 1, 1, 0. For the 5 it will be 1, 0, 1. For the 4 it will be 1, 0, 0. For the 3 it will be 0, 1, 1. One zero one zero 1 0 1 0 1 0. Fine. This is the output of these 3 flip-flops, and this is recycle, because the cycle will repeat unless you will apply clock pulses. So if this table is in your mind, then it will be easy to draw the timing diagram. I am trying to draw the diagram here in this space only by following the table. So if you have this table in your mind, which is just representing the decimal numbers which are going to count starts from 7 to 0, and the respective output of all the flip-flops starts from 7 to 0. Now whenever you will go with the timing diagram, you have required the representation of clock in terms of wave. Since you have 8, you have to count 8 digits, so the number of clock is 8. The following age 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. Why 9? Because this is the ending of this 8th clock. Fine. Now you will have to represent these 3 outputs of the flip-flop in terms of wave, and firstly I am taking QA. QA. Then I will represent QB and then QC. See, always try to make this pulse having same width. So just to make it in same width, trying to make it as in the dash form, just to make it in symmetric form. Since you are going to represent the output of 3 flip-flops, so it will be easy if you are using these dash. Fine. Now here you have, if you are clear with the working of these 3 flip-flop, then by keeping the working of this flip-flop you can draw the waveform. Meanwhile, if you want the following this table, then you can also follow this table. So see, starts with QA. Initially the QA is set at 1. So for the first clock initially for the first clock it will start at 1 and for the second clock it will be 0, then 1, then 0, then 1, 0, 0, 1. This is the representation of QA in terms of wave. Fine. For QB it will 1, 1. So for the first and second clock, first and second clock it will be 1, 1. For the third and the fourth clock it will be 0, 0. Again for the fifth and sixth clock it will be 1. For the seventh and eighth clock it will be 0. This is the representation of QB. Similarly, the QC, QC 1, 1, 1, 1. For the four first clock it is 1. So 1, 1, 1 and 1. And for the last 4 clock it is 0, 0, 0 and 0. This is the concept of waveforms for all the outputs. Now see, for the first clock, that is from here to here, QC is 1, QB is also 1 and QA is also 1 from till here. Now what about the next clock? For the next clock QC is 1, QB is also 1 while QA is 0. This is for the next clock duration. Now come to the third. Here QC is 1, QB is 0, QA is also 1. So this is 1, 0, 1. Now again QC is 1, QB is 0, QA is also 0. This is for fourth cycle. Next QC 0, QB 1, QA is also 1. For the next QC 0, QB 1, QA is also 0. For the next QC 0, QB is also 0, QA 1. And for the next all the three 0. So see, again the same concept. The circuit starts to count from 1, 1, 1, that is 7. Then it will come to 1, 1, 0, which is 6, 1, 0, 1, 5, 1, 0, 0, 4, 3, 2, 1, 0. So the cycle repeats until you will applying the clock. 7, 6, 4, 5, 3, 2, 1, 0. 7, 6, 4, 5, 3, 2, 1, 0. Just because this is a 3-bit asynchronous down counter. So by applying only one single clock at the flip-flop A, you can operate the whole circuit because the remaining flip-flop will get their own clock from the previous flip-flops. Fine. So you must have the idea about the proper definition or proper difference between asynchronous and synchronous counter. So the asynchronous down counter, for the designing of 3-bit flip-flop, 3-bit counter, you have 3 flip-flop. After the proper operation of the 3-bit counter, you must have idea of this table, and once you are clear with this table, it will be easy to draw the timing diagram of the 3-bit flip-flop, 3-bit counter. So hope you are clear with the concept of asynchronous down counter. By designing the 3-bit asynchronous down counter starts to count from 7 to 0. Now try to design 4-bit asynchronous down counter by following the same concept. The same concept if we follow, instead of using 3 flip-flops, now you will have to go with 4 flip-flops A, B, C, D. Instead of 3 outputs, here we will have one more output, that will be QD, because the 4th flip-flop is flip-flop D. So by following the same concept, try to design 4-bit asynchronous down counter for the counting of 16 numbers, starts from 15 and end at 0. Fine. Try to design your 4-bit asynchronous down counter, and you will get any doubt related to this topic during the designing your own counter, then mention your comment in comment box. Fine. Thank you.